Hi all. In the next few lectures, we will be looking at concentration inequalities for sequential processes. You can think of these as means to control the fluctuations of entire paths of sequences of random variables. And in this context, uh, an important topic that we will present is called uniform deviation bounds, and we will also explore the connection of these uniform deviation bounds to what is called the law of the iterated logarithm, which is a well known result in probability theory. So let's start with a simple motivating example. This is the example of sequential testing. Okay, so what is a typical sequential testing problem? Let's say we are thinking of a sequential testing problem about the mean of a Gaussian distribution. So let's say you want to test if an unknown Gaussian distribution's mean is either positive or negative to the right side or to the left side of 0. Moreover, let's assume that we know its variance. So let's say its variance is unit variance, and we would like to test as soon as possible sequentially and adaptively by drawing IID samples from this unknown Gaussian distribution whether each of these hypotheses is true, that is the true mean is either positive or negative. So more formally speaking, here is what you as a learner or a testing algorithm would do in order to solve this problem. So this is the protocol. At each time indexed by t, so you as a learner or tester, you can decide to stop at this time t. So if you decide to stop, so you can either stop or take one more sample. If you decide to stop, and this is based on past samples, based on everything you've seen in the past, you can decide to stop. Past samples. Then you're also required to guess or decide which of these situations is actually active, whether the mean is positive or negative. So you output a random variable a, which is your guess, and let's say that by convention you set a to be 1 if you believe or if you think the mean of the Gaussian is non-negative, and you output 0 if you think the mean is negative. Okay, and after you output this, you break this loop. Else you request one more IID sample, a fresh IID sample from the unknown distribution. So you get to observe a new independent sample. Let's say we call that xt, drawn from a normal distribution with unknown mean mu and known variance 1. Okay, so this is the decision making loop. A essentially represents your answer, or guess. So typically, a good sequential procedure is a procedure that takes as few samples xt as possible and outputs a, which is a correct answer with high probability. Okay, so towards this, let's formalize the requirement from such a sequential hypothesis testing procedure. Let's define tau to be the time, the random time at which the procedure stops and also outputs an answer a. So it's the first time that the stop condition is invoked by the algorithm. And a basic performance requirement from any algorithm is this correctness requirement, or in other words, we'd like the misclassification probability of the answer returned by the algorithm A to be always less than equal to delta. So here's a mathematical way of writing it. for any value of the true mean of the distribution that is generating samples. If you run this algorithm, when all the samples provided to it are drawn from a normal distribution with mean mu and variance 1. So, you run this algorithm and wait for it to stop, and you look at the answer A, the random answer A that it outputs. So, if A equal to 1, that means the algorithm stops and thinks that the mean is larger than 0, but the actual mean is less than 0. So, this event, or the event where A is returned to be 0, but the actual mean is greater than or equal to 0. So, both these are error events. Only one of these can occur depending on the actual value of mu. So, in any case, the probability of such an event is required to be bounded by at most a given number delta, say delta equal to 0.1 or 0.01. Okay. So, the decision, the design choice here is when to decide to stop, and if the algorithm has decided to stop or break this loop, what is the hypothesis to output based on all the data that has been seen so far, or all the samples that have been collected so far, right. So, a common way to build correct stopping rules which essentially satisfy this requirement. So, let's call this correctness requirement star. So, one way to build a stopping rule that respects star given a target parameter delta is to use what is called confidence intervals for the unknown parameter that governs the distribution of the samples. So, what do we mean by confidence intervals? So, here is a definition of here is one possible definition of a confidence interval sequence. So, a confidence interval sequence is nothing but a family of functions, one for each value of sample index, one for each let us say n sample number of samples n, that maps. So, what does it take as input and what does it give as output? It maps n samples seen so far. We denote it by x1 through xn and use x superscript n subscript 1, and outputs an interval in. Okay, so in is a real interval of real numbers with lower index called ln and upper index called un. So, we will assume in general that it is a closed interval of this form, subset of R, such that the following property is satisfied. For any stopping time or any stopping rule, so we already defined tau as a stopping time. Tau. So, recall that tau can depend on the data, on the xi sequence, and for all values of the distribution parameter that governs the probability distribution of the samples, we must have that the probability. Okay, so P mu is shorthand notation for the same thing, that is probability where all the samples, each successive sample is generated IID from n mu 1. The probability that the interval I at time tau actually contains the real parameter mu is at least 1 minus delta. Okay, so this is basically a coverage property. It says that no matter when you decide to stop, or no matter under what kind of stopping rule when the algorithm decides to stop, I of tau, the interval I tau, which is L tau comma U tau, the set of all numbers which are at least L tau and at most U tau, must contain mu with significant probability. Okay. So, note that a confidence interval sequence is an entire family of intervals. So, for any given n, it is desired that there is a interval in such that whenever you happen to stop at time n, in must contain tau, must contain mu with high probability. So how do confidence interval constructions help design good sequential tests? Here's the connection. So if we have a valid confidence interval construction with the probability of failure no more than delta as above, then here's a good sequential testing algorithm for the Gaussian mean testing problem. Okay, so here's what such an algorithm would do. The algorithm would stop at the first time t when 0 falls out of the interval it, that is when the interval it does not contain 0. So recall that the interval it is at time t comprised of a lower endpoint lt and an upper endpoint ut. So if lt ut is either to the right of 0 or to the left of 0, that means if either lt is larger than 0 or ut is less than 0, then you stop and you output the natural decision. That means if the lower endpoint of I tau, when you stop at time tau, L tau, if it's larger than 0, then you guess that the mean of the Gaussian distribution is larger than 0. If it is, if the upper endpoint U tau happens to be less than 0, then you would naturally guess that the mean of the Gaussian you're dealing with is less than 0. Okay. Let's call this a rule, an algorithm. So this gives you an entire algorithm for performing sequential testing and stopping when required with confidence. Okay. So why does this work? So what is the proof that this kind of procedure actually has a misclassification probability which is bounded at most by delta? Well, it's easy to see this. Let's assume for the moment that if the real mean of the Gaussian generating the samples is actually negative, let's evaluate the probability that the answer returned at time tau according to the rule above when you stop is equal to 1. So this is the error event when mu is actually negative and the answer output is actually that the mean is positive. So in other words, this is just p mu, that the lower endpoint of the interval I tau, that is L tau, is larger than 0. So we can break this sum into two parts by the law of total probability. So this is p mu L tau greater than 0 and mu belongs to I tau plus the probability of the same event intersected with mu not belonging to I tau. Now the probability of the first event is actually 0, because if this event were to occur, then it means that mu is at least L tau, but L tau is at least 0. So mu is greater than 0, which is not possible because mu was assumed to be less than 0. And so we are left with only the second term, for which an upper bound can be obtained by just dropping the first event inside. So this is just upper bounded by the probability that mu does not belong to I tau, and we know by the confidence interval property of the sequence of intervals I1, I2, I3 and so on, that this event occurs with probability at most tau. Okay, so the condition star, which is the correctness condition, so we call the star condition the misclassification probability condition, is met. Okay, so what we have seen is that good confidence interval constructions or valid confidence interval constructions, when coupled with the natural stopping rules, yield non-trivial hypothesis, sequential hypothesis tests. Okay. So how do you go about constructing confidence intervals? So this is what will expose the connection between confidence intervals and uniform deviations of stochastic processes. So let's perform the following thought experiment. So let's take a set of these random variables. So let's take the first n successive rewards generated by the distribution, okay, the unknown Gaussian distribution. So fix. So let's say let's first fix an integer n, okay, a non-negative integer n, since the first n samples, okay, so just think of the first n samples returned by the of the Gaussian distribution out of the infinitely many samples that are possibly generated. This has no relation to what samples were actually consumed by an algorithm. So, we are just thinking of the first n samples for a fixed small n. So, since x1 through xn are drawn assumed to be independent and identically distributed as a normal distribution with mean mu and variance 1 by Chernoff, by the Chernoff bound, we already have that p mu of let us say the sample mean 1 over n summation I equal to 1 to n xi minus mu exceeding epsilon, a level epsilon, is bounded by 2 e to the minus n epsilon square by 2. So, this is the standard Chernoff bound for a Gaussian. Okay, let us for shorthand denote the sample mean of the first n samples as x bar n. Okay, so this means that, so this is the say this in fact means that if I set a particular value of epsilon to make the right hand side equal to delta, so this is what we get. The probability that mu belongs to this particular interval x bar n minus square root 2 log 2 by delta divided by n to x bar n plus the same deviation 2 log 2 by delta over n. This probability is at least 1 minus delta. Okay, so this holds for any fixed n. Okay, so if there was a stopping rule that decided always to stop at time small n, okay, so never stop before that or after that. So, let us say there was a stopping rule that always stopped trivially at time small n, then this interval in with left endpoint as this number ln and right endpoint as un. Okay, so this interval would be a valid confidence interval at that specific time small n. Okay, so this is a 1 minus delta confidence interval. So, let us record this by saying that a confidence interval with level 1 minus delta for mu after having observed exactly n samples, where n is some fixed non-random integer, n samples is this interval. So, x bar n minus square root 2 log 2 by delta divided by n to x bar n plus square root 2 log 2 by delta divided by n. Okay. So, the key thing here is that the n samples are fixed. Okay, so this is sort of a confidence interval for a fixed or a batch. So, this is like a batch of n IID samples. Okay. So, however, if you have a stopping rule that actually stops at a random time depending on the data, so at a random, possibly data dependent, that means depending on the previous history of samples observed so far. So, let us say someone has designed a stopping time tau that is sort of non-trivial. Okay, so it's maybe complicated. Maybe you stop at the first time when the certain property of the sequence of samples seen so far has been satisfied. So, that could lead to various a distribution of the stopping time tau. not necessarily always at a fixed number of samples n. Okay. It's not hard to argue that the set of samples that you've seen until stopping x1, x2 and so on up to the last time a sample was taken, that means x1 through x tau, the tau samples, in fact these are no longer IID in general. Okay, so these need not be IID in general. Okay, so this is probably a surprising fact the first time you encounter it, but on the other hand, it's not hard to come up with some counter examples to x1 through x tau being IID. So basically, the upshot is that in the previous setting we considered n to be a fixed batch of samples. So this is equivalent to saying that there is a stopping rule for which tau is exactly equal to n always. It always stops after taking n samples, no less, no more. And so in that case, naturally x1 through xn by definition are going to be IID. But if the stopping rule actually depends on the data seen in the past, then the IID property is can be completely violated. Okay, so just as an example, you can think of a rule which is quite strange in the sense that it says, let's wait, let's stop when you see a sample larger than some value, let us say 10, for the first time. Okay, so it obviously means that the sequence of samples you have seen so far has the property that the last sample x tau is going to be greater than or equal to 10, and all the previous samples are by definition going to be less than 10. Okay, so this is not an IID distribution over samples x1 through x tau. Okay, but so this sort of violates the ability to apply Chernoff, because as we know, Chernoff requires tau to be non-random. So you can't okay, so you couldn't have applied Chernoff in the setting earlier when small n was random. So think of a random number of samples being taken, which can actually depend on the samples themselves. So if small n was actually a random variable, you would not be able to apply Chernoff for obvious reasons, because Chernoff requires, number one, all the random variables to be independent, and number two, there is this n that appears on the right hand side, so you can't have n as a random variable. Okay, so so this is a sort of subtle but important issue that one has to worry about when defining concentration events for sequential procedures or sequentially sampled processes. So the one obvious way to get around this problem is to use a union bounding argument along with Chernoff. Okay, so the idea here is that you can build uniform deviations concentration bounds by using the basic union bound idea from probability. Okay, so what do we mean by this? So suppose we want to construct confidence. You want to construct a family of confidence intervals, one for each time, such that no matter what the value of tau is, the interval at the stopped time I tau contains mu with high probability must hold. So here's what you do at any for any stopping time. Stopping time induced by a stopping rule, and we define mathematically the stopping time to be tau. Okay, we will make the small technical assumption that tau is almost surely finite, assuming tau is less than infinity almost surely. So as long as tau is less than infinity almost surely, one can do the following, one can write the following. So the probability, so I am omitting the subscript mu, which is because that is understood. The probability that the absolute value difference between x bar tau, so imagine that you have stopped at time tau according to some data dependent rule, and x bar tau is the mean of the first tau samples that you have taken before stopping. So the probability that x bar tau minus the real mean mu exceeds let us say a number epsilon tau that we will design later. So let us think about the probability of this event. Okay, so we know that tau is less than infinity almost surely. So what this event implies is that there must exist a value of I, where I is any positive is some positive integer, such that the absolute value difference between x bar I, the first I samples average, minus mu, must have exceeded epsilon I. Okay, this is just by basic inclusion. So there is no way that the first event would have happened if the if not for the second event. Okay. Okay, so at some point in time tau, if your sample mean of tau samples exceeds is further further from mu than by an amount epsilon tau, that it means that there must exist some integer I at which x bar I minus mu is greater than or equal to epsilon I. And by the union bound, you can bound this probability by summing over all possible values of this time tau. Okay. Of the probability that x bar I minus mu exceeds epsilon I. Okay, epsilon I is something that we are yet to define. So let's try to arrange things so that this final sum that we have here, the sum from I equal to 1 to infinity, is no more than delta. Let's say we are given a target value of delta for the coming up with a confidence interval construction. So if the ith term in the sum above is, let us say, less than equal to let's just say delta over I square. So delta is the number, the probability, the violation probability number we've been given, and let's probably try to find epsilon I such that each successive term is bounded as delta over I square. Then by summing all these, 1 over I square is a summable sequence. Sum is, for instance, less than some constant times delta. Okay, the constant is whatever you get when you sum 1 over I square. Okay, so what is this? So what is our target? We want to make probability xi bar minus mu greater than equal to epsilon I less than equal to delta by I square. Okay, now we have fixed. So I is a fixed integer here. Okay, there is nothing random about this integer I. So x bar I is simply now the sample mean of I, the first IID samples from a Gaussian with the mean mu. And so here is where you can actually use Chernoff. So by Chernoff, an upper bound, so this is implied if the Chernoff upper bound, which is 2 e to the minus I epsilon I square by 2, can be made less than delta by I square. And this is just the same as saying as setting epsilon I to be equal to square root 2 over I log 2 I square by delta. Okay. So right. So what we have shown by this union bounding argument along with Chernoff is that even for a random, no matter what the value of the stopping time tau, you are assured that the interval I tau, so you can set I tau as x bar tau plus minus, the lower endpoint being the minus and the upper endpoint being the plus, square root 2 over tau log 2 tau square by delta. Okay, so you have an interval at stopping, and then you can basically make a decision based on whether 0 is in this interval or not. Okay, so the usual theory carries forward. So let's think about this union bound result we have shown from a slightly different viewpoint. So in other words, what have we shown? What have we shown? We've shown that the probability that for any positive integer I, xi bar minus mu less than equal, so in fact for all I less than equal to n, for all I natural numbers, the probability of the deviation of xi from xi bar from mu being less than 2 over I log 2I square by delta is greater than or equal to 1 minus delta. Okay, so uniformly over time. So for all I natural numbers is just saying uniformly over time, the sample mean xi bar, so xi bar minus mu always stays within this fixed I dependent number on the right. Okay, put slightly differently, this is also equivalent to saying that the supremum taken over all I positive integers of, so if you divide the left hand side by the right hand side, then it's at most 1, and it just says that the supremum of square root I times xi bar minus mu divided by square root 2 log 2I square by delta is less than or equal to 1. This entire event has a significantly large probability of 1 minus delta, of at least 1 minus delta. Okay. So just to pictorially illustrate, so this is so let's illustrate this statement with something that conveys the nature of fluctuations of the stochastic process x bar I. Okay, so so for instance, here's one way of representing this result. So on the x-axis we have I. Let us so in fact one remark here is that the denominator here. So imagine delta to be fixed. Delta is a fixed number. So order wise, this is basically nothing but square root log I. Okay, so let's plot square root log I on one hand. So if I starts from 1, then this is how square root log I looks, and on the negative side, this is how minus square root log I looks. Okay, and this is sort of the region in between. So let's think about the path of the entire stochastic process indexed by I, which is square root I times xi bar minus mu. Okay, so all we are saying is that with probability at least 1 minus delta, the stochastic process given by I times square root I times xi bar minus mu, okay, over all integers I is contained within this shaded yellow region. Okay, so there is this tube, if you wish. So this is sort of a tube that is bounded by the functions roughly square root log I and minus square root log I, and what we've established by this very basic union bounding argument is that if you basically take a scaled version of the difference between the sample mean and the true mean, scaled by basically square root the number of samples, and plot that trajectory, okay, then a typical trajectory is going to sort of wander always within this tube. Okay, so that's what we've shown. Okay, so this is in some sense to be regarded as a statement about the trajectory of the entire stochastic process, square root I into xi bar minus mu, for I equal to 1 to infinity. Okay, so it's an infinitely long, infinite time stochastic process. Okay, so that's what we've shown. So this raises the question of how much we can actually improve things. Okay, so can we actually try to, if you're given, you know, a 1 minus delta high probability target, what is sort of the narrowest kind of green tubes that you can draw to bracket the entire trajectory of this stochastic process with probability at least 1 minus delta. Okay, and that's the that brings us finally to the subject of controlling uniform deviations or time uniform deviations of a stochastic process right from time 1 to time infinity. So here's a natural question. We saw that if, for instance, in the mu equal to 0 case, so when xi are all drawn, xi is a sequence of IID, infinite IID random variables drawn from the standard normal distribution. Then we saw that the probability that the largest possible value of this ratio, which is absolute value of Sn divided by square root 2n log 2n squared by delta. Sn is nothing but the sum of the first n random variables xi. Okay, so we have just represented xi bar as Si divided by I. Okay, so what we saw is that Sn, okay, you can think of Sn as a random walk. The magnitude of Sn, if you scale it by square root 2n into log 2n square by delta, that quantity is never going to hit 1, cross the level 1 with probability at most 1 minus delta. Okay, so basically it says that if you draw in the Sn sense, if you draw two tubes of plus minus square root roughly n square root n log n, then Sn is not going to wander outside this tube ever unless you are in an event of probability at most delta. Okay, so the natural question here is can you do something about this denominator? By how much can the denominator be improved or increased? Okay, so if you want tighter control of, if you seek tighter control of Sn, let's say, then it means that you would want to try to raise the level of the denominator as much as possible as a function of n and delta. So by how much can the denominator be improved or increased for uniform deviations to be under control? Okay, by uniform deviations, we basically mean the supremum over all positive integers. Okay, so this is what we will show to this effect. It turns out that there is a sort of, in some sense, large room for improvement compared to what we've got so far. So we will show the following result in this lecture. So we will show, in fact, that in the usual situation, let us say without loss of generality, that all the xi's are drawn IID with a standard normal distribution. Then the probability of the worst case ratio of between Sn and a quantity that is roughly order square root n. The square root n is inevitable, but what we will be able to do is we will be able to replace the polynomial n sitting inside the log by a logarithmic n. So we can actually get log n as a function of n, exceeding being less than 1 to be at least 1 minus delta. Okay. So this is the result that we will be able to show in contrast to the previous result. So instead of log n in the previous result, so there is a polynomial n sitting inside the log, which is roughly equivalent to log n. We will be able to actually get log n deviation as a multiplier for the square root n. Okay, and this is actually, if you think about it, this log n compared to the n square on top is an exponential improvement. Over n to the alpha or poly n. Okay, so n square like this, for instance. Okay, that you typically get by doing a union bound over the entire time horizon. Okay, so one may wonder, is this the only is this the limit of how you can how far you can go? Well, in fact, in some sense, the answer is yes. This is the best possible result that you can show to that you can hope to achieve in the sense of controlling uniform deviations of Sn. So, in a sense, because there is in some sense a lower limit or a fundamental limit to how far you can go to control uniform deviations due to what is called the law of the iterated logarithm. LIL. And here's the statement of the LIL for the same setting where you're dealing with sums of IID standard normals. So the LIL basically says that for xi drawn IID from normal 0 1, the probability that the lim sup as n tends to infinity of Sn. So if you scale Sn by square root, basically roughly root n log n. Okay, the probability that this lim sup equal to 1, or the on the symmetric side, if you take the if you take the probability of the event that liminf as n becomes large of Sn scaled by square root 2n log n equal to -1, these are actually almost surely true. Okay, so these are actually events that happen with probability 1. Okay, so what this says, again with respect to the figure, is that um, if you so it doesn't matter how you draw things. If you draw uh, square root 2n log n, and on the bottom you plot the envelope of minus square root 2n log n. Okay, what it says is that what this law of iterated logarithm says is that infinitely often the process Sn is going to touch both these boundaries. Okay, it's going to come arbitrarily close to both these boundaries. Okay, so basically, if you bump things down by a factor of 1 minus epsilon, let's say, where epsilon is small, then it means that infinitely often, with probability 1, the process Sn is going to wander out of this tube infinitely many times. It cannot be constrained within this narrower tube. Okay, so this sets an absolute lower limit, because there is an almost sure event that the process Sn is going to breach these the boundary of such a tube with such widths, and so one cannot hope to really improve the scaling of the denominator better than square root n log n. Okay, so what we are going to show here, this result can be thought of as a uniform deviations or finite time analog of the law of the iterated logarithm. The law of the iterated logarithm is really a statement about it's an asymptotic statement about the nature of the sequence Sn. Okay. So let's go ahead and try to derive this kind of best possible bound, which is basically expressing uniform deviations of the Sn process. Okay, so that will be the last part of this lecture. So what is the basic idea here? The basic idea is, so recall how we got the weaker bound with the square root n log 2n square by delta. We basically did a union bound over all values of time. Okay, so in contrast, the idea that I'd like to present here to get sort of almost optimal LIL type uniform deviation bounds is to save on doing so many union bounds. So save on doing a global union bound over all values of small n over natural numbers. Instead, we'll use what is called a peeling argument or a peeling trick. This is sort of the name that has become sort of standard for this kind of procedure by now. Which involves, broadly speaking, much fewer union bounds. over much fewer instance of time. Okay, so here's so maybe let's set up some notation before I describe the idea in more detail. So let's fix some epsilon, a constant between 0 and 1. You can think of epsilon equal to half, for instance, for the remainder of the proof, and that so let's define u0 as time instant 1, and let's define the k plus first instant next time instant as 1 plus epsilon times uk for all k greater than 0, greater than equal to 0. Okay, so u0 is 1, u1 is 1 plus epsilon, u2 is 1 plus epsilon of u1, and so on and so forth. In fact, technically we need all of these to be integers, so it's best to take the ceiling. Okay, so this is sort of the precise definition of these UKs. These are also a subset of the natural numbers, and to convey the entire idea of peeling using a picture, here is the set of all times at which you want to control uniformly the deviations of Sn. So it starts with time 1. Okay, so that is u0. u1 is here. u2 is basically a geometric is sort of a scale factor 1 plus epsilon times u1, and so this grid uk basically grows geometrically as a function of k. Okay, it explodes rapidly. So it's a geometrically increasing grid u4. Okay. So in order to, so we have a process S1, S2, S3 and so on, which is taking values at every possible natural number. The UKs are a subset of these natural numbers. Imagine that you can control, imagine that you want to be able to control the fluctuations of the stochastic process Sn by first controlling Sn at these chosen points UKs. Okay, so first let's say that we want to be able to control Sns at only these UKs. So these UKs are much, in some sense, far fewer numbers than the entire set of natural numbers. So we'll first control Sn at n equal to u1, u2 and so on, and then locally handle Sn between each, let's say, uk to uk plus 1. Okay, so in some sense it's a hierarchical approach. This peeling approach, that's why it has the name peeling, because you sort of it's a hierarchical approach where you first control, you basically block, you bunch time up into exponentially increasing segments. You control the process at the endpoints of each segment, and then do a sort of a separate local procedure to control the deviations of Sn within these segments. Okay, so we'll see exactly how this idea pans out. So at least in the process, the total number of union bounds at the outer level over the UKs is in some sense going to be much smaller than taking union bound over all natural numbers, and that's sort of the reason behind why you get this exponential improvement in the end. Okay, so this proof that we will present using the peeling argument, it occurs in several parts, several places in the literature on statistics and sequential statistics and online learning. But we will use the argument that is given in this paper by Jamieson et al., which is basically an online learning paper featuring what is called the LIL-UCB algorithm for multi-arm bandits. So so let's do this peeling argument in detail. So let's define this function for convenience, Cx as roughly square root x log x by delta. This is the kind of uniform deviations growth that we want in our result. So there are 3 steps to the argument. So step 1, Step 1 is the control, the first level of the hierarchy. So this is the control of SUK for all k, and let's see how we do this. So we just want to bound, let's say, the probability that there ever exists a value of k for which SUK exceeds let us say square root 1 plus epsilon. So you should just think of the square root 1 plus epsilon as just some number larger than 1. Okay, that's all the meaning of that's all there is to the meaning of this epsilon. Epsilon, you can just think of epsilon conveniently as a half into C of u of k plus 1. Okay, C of u of k plus 1 is in some sense a threshold that we want to control every SUK by. So we can first split this by the union bound over these k's. Okay, which are much smaller than the total number of, I mean, in some sense they are smaller than the total number of natural, they avoid many natural numbers and many union bounds, potentially wasteful. E raised to minus 1 plus epsilon log of log uk plus 1 divided by delta. This is just by using the union bound and also simultaneously applying the Chernoff bound for Gaussians. So first using the union bound plus the Chernoff bound for Gaussians. Okay, so this is just a simple union bound followed by Chernoff. So this is the same as the sum. So by the way, I am avoiding I'm avoiding sort of more precise computations because uk plus 1 is the ceiling of 1 plus epsilon times uk. So we'll presume that you can use fractions for, you can use real numbers for integers, but with small modifications the entire argument goes through in exactly the same way as we are doing now. So this is exactly summation delta by k plus 1 log 1 plus epsilon, the whole thing raised to 1 plus epsilon. And the only part that depends on k, if you remove, you are left outside with delta by log. So let me write it here. This is delta by log 1 plus epsilon raised to 1 plus epsilon that comes out, followed by a sum of 1 by k plus 1 to the 1 plus epsilon. And by some bound integral bounds, you can easily show that this is at most 1 plus 1 by epsilon. So finally we get the bound of delta by, so let's write 1 plus 1 by epsilon into this quantity delta by log 1 plus epsilon into 1 plus epsilon. Okay. So you should really think of this complicated looking right hand side as just upper bounded by some constant times delta. Okay, so because delta is a number smaller than 1, delta to the 1 plus epsilon can obviously be upper bounded by delta itself, and the rest is just a constant 1 plus 1 by epsilon in the denominator, which is a function of epsilon. So it's just a constant times delta finally. Okay. Okay, so we now come to the second step, which is descending one step lower into the hierarchy and trying to do local control. So this is about controlling Sn for n in the interval uk to uk plus 1. Right. So how do we do this? We'll take recourse to the following result from probability called Hoeffding's maximal inequality. So we'll use the following result from probability called Hoeffding's maximal inequality. Which in our case applied to standard normal IID random variables. says the following. So for every integer m and x greater than 0, the probability that there exists an n in 1 through m for which Sn exceeds x. Okay, this is really the same as the probability that the max over n equal to 1 to m of Sn is larger than equal to x is actually controlled by basically the same kind of Chernoff exponent, Chernoff rate, as what you would expect for Sm, the last element Sn. Okay, and the reason this holds, you can go and look this up. This is a consequence of an even simpler stated but very powerful result called Doops martingale inequality, Doops submartingale inequality, in fact. Okay, so we are not going to prove this inequality in this class, but we'll use it as a statement of fact. So what it says is basically it allows you to control over a given interval of time m uniformly the supremum of a random walk Sn. Okay, so using this we can write the following. So we have that the probability. So using this, we have that the probability that there exists a time t in the interval between two epochs uk plus 1 all the way up to so this is a set of integers up to u of k plus 1 minus 1. Okay, since we have already controlled for uk and uk plus 1 separately at the top level of the hierarchy, st relative to suk. Okay, so think of suk. So going back to the figure here, think of suppose k is equal to 2. So you already controlled SU2, and we are trying to sort of understand how much fluctuation, excess fluctuation there is in this interval between U2 to U3. So ST minus SUK exceeds, let us say something again, square root epsilon into C UK plus 2. So UK plus 2 is chosen conveniently, as you will see soon. This is equal to the probability that there exists t. So just by by recentering time, you can just recenter everything from time uk onwards. It doesn't change the nature of the random walk. So there exists a t in the interval. So basically in 1 through uk plus 1 minus 1 minus uk. Okay, such that st exceeds square root epsilon c uk plus 2 as before. This is the same because all we have done is we have basically started time for the random walk from the time uk. So this is by recentering time. And now we can apply Hoeffding's maximal inequality. To get an upper bound of minus, so the square, so whatever is here gets squared. So epsilon, the square of c uk plus 2 is precisely 2 uk plus 2 log uk plus 2 by delta. And finally we have to divide by this by 2 times the number of steps in the random walk, which for us is just uk plus 1 minus uk. Okay, so right, so we have this upper bound. Now we can take this epsilon here and this uk plus 2 and this difference essentially between uk plus 1 and uk, and show that this ratio is lower bounded by 1 plus epsilon. Okay, so this is an easy exercise. So you can replace with 1 plus epsilon. So this is basically the reason why the geometric gridding works. It essentially says that there is a factor of 1 plus epsilon increase in the sort of scale, and at the same time it also saves you many union bounds at the top level. There is an exponential reduction. So log uk plus 2 by delta. The reason for this is in short that epsilon uk plus 2 divided by uk plus 1 minus uk minus 1 can be shown to be greater than or equal to 1 plus epsilon. There is always a ratio 1 plus epsilon here. Okay, and this in turn is just simply expressed as delta over, using the definition of uk plus 2. uk plus 2 again is basically 1 plus epsilon raised to k plus 2 up to a small approximation. So ignoring that approximation error, we can just write this as delta over. So log uk plus 2 is just k plus 2 log 1 plus epsilon. Okay, and the entire thing is raised to the exponent 1 plus epsilon. Okay, so this is again essentially a constant times delta. This is another constant times delta, and so we have essentially managed to bound both local and global fluctuations of Sn by basically constant times delta, and the last step is to just put both of these together. So to get the LIL type result. So putting everything together. So this is the last step. So by steps 1 and 2, we get that. So steps 1 and 2 essentially give you probabilities of bad events upper bounded by some numbers. So here's the good event, this is the complement with probability at least 1 minus the total bad events. So step 1 gave you a bad event probability of this much, and step 2 gave you a bad event probability of this much. Okay, so we can argue that if you sum up the bad event probabilities and subtract them from 1, so step 1 gives you basically 1 plus 1 by epsilon into some expression, and then a further 1 by epsilon into this thing. Delta by log 1 plus epsilon raised to 1 plus epsilon. So recall that in step 2 you have to sum over all the all k's to get the net bad event of step 2, that any of the local fluctuations is bounded. So with this much probability for all epochs k and for all time steps, local time steps within the epoch k, so the right endpoint is now included thanks to the step 1 result. We must have that St. So can we bound St finally? St is actually St minus Suk plus Suk, and each of these terms is bounded. The first one by step 2 and the second term, the difference by step 2 and the last term by step 1. So we know that by step 2 this is at most square root epsilon c of uk plus 2, and the second deviation is bounded with high probability by square root 1 plus epsilon c uk plus 1, and we just need to do some very basic algebra and bounding. So we know that t is within uk to uk plus 1, and so uk plus 2 must be at most 1 plus epsilon square into t, and c is a monotone function, plus square root 1 plus epsilon. Again you can bound uk plus 1 by at most 1 plus epsilon times t, Okay, you can use a further bound on square root 1 plus epsilon of 1 plus square root epsilon, and finally you get something like 1 plus 2 square root epsilon c of 1 plus epsilon the whole square, which is another constant, times t. Okay, so the orders are all essentially in the right place. So for instance, so this essentially completes the argument. If you specialize and write this, for instance, with epsilon equal to half, if we take, say, epsilon equal to half and write down this result, then the probability that there is ever a time uniformly over the entire time horizon where Sn exceeds 1 plus square root 1 plus 2 square root epsilon, that's 1 plus square root 2, into the square root of let's say twice 9 by 4, that's 1 plus epsilon the whole square, and log of 9 by 4n divided by delta. So that gives you the log n type term, is no more than 1 plus 4 into some constant into delta to the epsilon by log 3 by 2 raised to 3 by 2, which is ultimately some constant, some explicit numerical constant times delta. Okay, and which is essentially in the form of the it's a finite time version of the law of the iterated logarithm. Okay, and the key idea here was to use this kind of hierarchical peeling idea, or peeling trick as it's commonly called, to essentially try to save on the number of union bonds, getting as close to optimal as possible. Thank you.